Good morning, everybody. Oh, we're on fire this morning. And welcome back to those of you that, some of you were here yesterday. It will be different today. And the observant amongst you today, who were here yesterday, may have noticed I wasn't sporting this beautiful accessory. I wasn't put under house arrest overnight. It tracks me on the camera, apparently. So I'm going to be very self-conscious with it. I'm going to talk today about largely about understanding of the four fluencies. So yesterday, the focus for those of you that weren't here was on reasoning with a bit of attention to problem solving. I'm not saying that I don't think fluency isn't important. I really do think it's important. Is there a hideous echo at the back? Is it just at the front? Yeah. I don't know how I control that by staying away from there, I think. And today I want to share some thoughts on understanding and how working with the big idea behind behind what we're going to be talking about. Hello. Is how are there some core ideas that run through the years of schooling so that maths is seen not as a sequence of new topics that kids are forever learning, but a continuity of ideas that we can build on. So I want to reduce our load as teachers, and we've got people on the stairs. There's loads of seats on this side, and I won't embarrass you too much as you walk past the front. Karen, could you just go and see if the technical woman is around just to sort out the sound? Because I think it might be unpleasant by the end of the morning. Good morning. Hi, Stanley. Hi, labelless man. Hello, man with it under his sweater. Hello, man with his lunch ticket. Okay. Understanding. So very briefly, there's lots of talk about big ideas. Di Seaman, some of you will, I'm sure, know her work. She's done a lot of work on big ideas. So there's a range of interpretations of what we mean by a big idea. The definition, what I'm holding to with a big idea is that I want ideas that are mathematically big and conceptually big. Ideas that glue mathematics together and ideas that glue students' understanding together. And so I'm looking for ideas that connect together seemingly disparate mathematical ideas. So I think we don't do enough of connecting together measuring with teaching fractions. That if we put those together, they're one and the well, they're not one and the same, but they connect together. That fractions and division connect very closely together, and if we teach fractions as a form of division, we're reducing the load that kids have to learn, and reducing the kind of scope of the mathematics. And linked to that is this conceptually connecting idea that they help kids glue things together. I want them to have currency across several years of schooling. I want the continuity of progression. I want students to get to revisit them so that they can build and grow their thinking. And I want them to promote inclusive classrooms so that, is that what we do there? So that we, okay. All right, can you still hear me at the back? Okay. Good. Less bleeding ears at the back. Yes. Good. And so if I've got this view of progression in ideas, students can engage with them at different levels. So I can have inclusive classrooms. Again, if you want to shuffle across in front of me, people on the stairs, do feel free to come and find some seats over on that side. But if you're happy there. I'm not going to talk about all of these, but some of the big ideas are things like a position on the number line, which you might think, well, isn't that just a kind of technique? But I'll talk a little bit about that. Equivalence, pattern, of course, is a really big idea in maths. Place value, the idea of symbols and what they mean, estimation. I do think estimation is something we don't do enough of in our teaching. And I think we sometimes, kids seem to get some very strange ideas about estimation. I know when I was at school, whenever I was asked to estimate the answer to a calculation, I never did that. What I always did was I did the calculation and I took 10 off. Because I didn't want my estimation to be too wrong. And there's some evidence that kids think there's a right answer to an estimation question. If you say, can there be two answers to this estimation question? They go, no, maths only ever has one right answer. I think in these days of technology and being able to get your technology to do your maths, estimation becomes even more important. I don't think I mentioned this anecdote yesterday, but I don't know if you saw it. There was a little YouTube video went viral in South Africa a few weeks ago. It was a Scottish mother who had sent her son off into the bedroom to do his maths homework, and she could hear him talking, and she thought it was very strange. He doesn't normally talk during his maths homework. She opened the door, and he's going, "Hey Siri, what's 7 times 8?" And Siri's going, 7 eighths is 56. Thank you, Siri. Hey Siri, what's 5 times 4? And he was getting his mobile phone to do all the maths for him. Arithmetical reasoning, I'm going to talk quite a bit about that and what I mean by that, and classification, how we sort things. So just a quick look at why I think positioning numbers on a number line is a big idea that we really need to think about. And I'm going to be talking about number lines quite a lot today because I think they glue together a lot of mathematical ideas. And the overall big idea is, of course, that the real numbers have a unique position on a number line. And that takes me through virtually all my schooling up till the middle of secondary schooling, if I'm playing with putting numbers on a number line. Because there are things like, it's a powerful idea because it links discrete and continuous quantities. That I can put the counting numbers on a number line, but as soon as I start to put the fractions in between, I'm linking things that I can count, like cows and bottles, and things that I can't count, like milk and moos, noise level of moos. I can only measure those, and so of course measurement is such a key idea that brings together the countable and the uncountable, that measurement and how do we record linear measurement? We record it on a number line. It's a really, really powerful thing for kids to be thinking about. There's lots of evidence that positioning numbers on the number line helps children understand lots of things about ordering and sequencing numbers. It helps you connect different representations. And importantly, there's lots of evidence that at all ages, the ability to mark numbers on a number line equally spaced is a predictor of later attainment in maths. And what I mean by that is, if you ask, I just need to get my number line the right way, so I need, what do I want? 0 to 10, is that right? Yes, 0 here. Yes, you're going to be 0 for me, okay? If you give young kids a blank number line and say, put the numbers from 1 to 10 on the number line, what often happens is they go 1, 2, 3, 4, oh gosh, I'm running out of space. And 8, 9, 10 get squashed up at this end. And the evidence is that happens all the way through our schooling. If you say to kids, put the numbers, multiples of 10 on a line from 0 to 100, they will squash up multiples of 10. And if you say to kids things like, here's a number line, and this is 0, and this is 1,000, where's 3 on the number line? They go, oh gosh, it's really, really close to 0. And you say, where's 996? And they go, oh, that's really, really close to 1,000. And you say, and where's 35? And they go, oh, it's probably about here. Because it's got to be a long way from 0. So getting this sense, and interestingly, one of the things I'm going to be talking about later is we tend, I think, to think that our kind of natural way into arithmetical reasoning is through addition and subtraction. There's lots of evidence from the psychology research that we're just as naturally inclined to think about things multiplicatively than we are to think about them additively. And these are the two big ideas I'm going to talk about at length. And what I mean by that is In one sense, numbers do get closer together as they get bigger. In the multiplicative sense, they do get closer together. What I mean by that is, if I've got a pile of 3 bricks here and 4 bricks here, I can see the difference between them. I can see the additive difference is a difference of 1. If I've got a pile of 103 bricks and 104 bricks here, I can't see that difference. So they feel closer together at a kind of phenomenological level. But also, if I think of those, if I'm comparing those quantities multiplicatively, those two are, in the multiplicative sense, closer together. What I mean by that is, if you've had 2 days at MAV conference and you're going out to a party tonight and you think, God, I've listened to that bloke twice, so I really need a strong gin and tonic. And you go to a party, and for some bizarre reason, there's two drinks stations at this party. At this drink station, there's a barman who is mixing 1 litre of gin to 2 litres of tonic water. Okay? And the barman over here is expecting a lot of business, so he's mixing 101 bottles of gin, litres of gin, with 102 litres of tonic water. Now, of course, the difference, yes, the man there, where you want a strong gin and tonic, who are you going to go to? Here, yeah, this is almost 50-50 in terms of multiplicatively. That's equal, almost equal gin and tonic. That's a way stronger hit of alcohol than I'm going to get over here. So, and that's kind of it's a natural way of understanding. And one of the things I also want to explore through this talk today is how we build on these kind of instinctive, almost intuitive senses of quantity that we have to help kids develop that through the years. So yes, so as I was just recapping what I said, that the number line links quantities we have to measure, and it was a big step through of mathematicians realizing that if they put measurement on a number line, that you can start to count the uncountable. And of course, in terms of progression through school, it looks like this, that in early years, I'm playing games jumping along a number track. I'm playing very simple games on a number track. For those of you who are involved at all with working with very young children, there's a nice piece of research by a researcher called Robert Slavin, who has got a very simple game that helps children who come into school behind their peers mathematically to catch up. And it's just a simple number track game. And all you do is this: you have a number track and a spinner or a dice with 1 or 2 on it, and the track goes from 1 to 10 initially, and then from 1 to 20, and you can move it up to 1 to 100. And you spin the spinner, and you move your counter along the track according to whether you've spun 1 or 2. And the winner is supposed to get to 10. It's the dullest game on the planet. But the way you play it with the kids, and you only have to play it with young children for about 10 minutes a day for about 4 weeks, there's a particular way you have to encourage the children to play it. And it's this, that if you're on space 5 on the track and you spin the spinner and you score 2, now if you're playing snakes and ladders, of course, what you normally do when you're in that position is you pick up your counter and you go 1, 2, oh, I'm on 7. What you have to work with the kids on is you pick up your counter. If I'm on 5, you pick up the counter and say 6, 7. So you have to do 2 things simultaneously. You have to hold in your head the fact you've got to make 2 jumps, but you've got to say the numbers you're landing on. That's why the spinner can only have 1 or 2 on it, because if you roll a dice and you get 6, it's too hard for young kids to hold, to keep track of making 6 jumps and to say the 6 numbers. But he's got lots of research evidence that if you play that sort of game with kids for about 4 weeks, for a couple of times a week for 10 minutes, kids who at 4 or 5 come in and are behind their peers in school catch up in their number understanding. And the effects are long-lasting. And later on, you can play it with larger numbers going up to 10. So work on a number track is really important in early years. Then I'm working on the number line, where I've moved from labeling squares to labeling positions on the line. So, of course, a number track doesn't have a 0 on it because it starts at 1, whereas my number line will have 0 on it. moving into putting fractions between those numbers on the number line, into the integers, extending it back into positive and negative integers, and then in secondary school starting to explore rational numbers and where they sit on it. And I've got an image there and a sense of ordering and playing and positioning numbers that takes me all the way through from being 5 to being 15 or so. Quickly thinking about fractions, two big ideas in fractions are that they arise from measuring and they arise from fair sharing problems. Now, I think we tend to teach fractions largely as though they are things. If there's one word I would try and get rid of in the curriculum, it's the word recognize. We talk about recognizing fractions. We never recognize a fraction. We actually have to construct it. Fractions aren't out there in the world to be recognized. They were made up by mathematicians to solve problems like 3 divided by 4, where there isn't a whole number answer to it. And so if we work on fractions as measures and fractions as equal, or fair sharing, I should say equal sharing there. Fair sharing can sometimes be, I'm going to give you the bigger piece because you're older than me. Equal sharing is where the fractions comes from. Then it takes me through. And so the two kind of examples of where fractions can come from in terms of developing these big ideas, these are kind of the generic problems which you can adapt for lots of different ages, are if a bar of chocolate is cut up into 3 pieces and Joe eats 2 of the pieces, how much of the chocolate does he get? That's the measuring. So what's happening here is that Joe is measuring how much chocolate he's eating by the basis of how much of a whole bar it is. So I have 2/3. And we sometimes, I think, lose the measuring aspect. I look back at my own teaching of young children some years ago and remember doing stuff like, the classic thing of having an apple and cutting it into 2 equal pieces and bringing one of the pieces out and saying, what fraction is this? And of course, what I want the kids now to say to me is, well, I don't know until you ask me what it's a fraction of. Because that's only a half if there was only 1 apple in the bag. But if I bring it out of the bag and say, what fraction is this of what's in the bag? Then if I've got 4 apples in the bag, the thing I've got in my hand is 1/8. So I'm measuring. It's not a thing. It's not an object. It's a unit of measure, and I need to know what my large measure is that helps me make sense of that. So I can't look at that. I can't recognize it and go, oh yeah, that's a half, because it's an incomplete question if I'm not saying it's a half of what. What are you measuring it against? And the second equal sharing is if Joe and 2 friends share 2 bars of chocolate, how much chocolate does Joe get to eat? Of course, the answer again is 2/3, but the research evidence is you get more mileage with kids out of working on the second type of problem than you do on the first, because in a sense there's 2 answers to the second problem that you can explore. One answer to the second problem is that Joe gets 2/3 of a bar of chocolate, or he gets 1/3 of the chocolate. So again, you have to be very clear about what your unit is. You can't say, oh, he gets 2/3. You've got to say 2/3 of what? And the evidence from research is that children, right the way through schooling, who have got this experience of constantly, when they're working with fractions, having to recognize what the overall unit is, that their understanding is much stronger later on. Here's one for you to think about. I've chosen fractions here which are sufficiently ugly to discourage you from putting them over a common denominator, I hope. Is there a way of working out which of those is larger without resorting to common denominators? Have a minute talking to the person next to you. Okay. All right, back to me. Now, if this was a kind of normal lesson and you were my class, what I would be doing while you were having that conversation is going around, not helping people, but listening to what they're saying. Those of you that were here yesterday, I talked a little bit about variation theory, which is the importance of contrasting things. And how it applies to this is, as I'm going around, I know that there are two possible arguments that people often come up with, and I'm listening for those two arguments, and then I'm going to invite my learners to share them. So here's the two that I expect have been rattling around this room, rather than getting them from you, and it's this. So the first, this is kind of the baseline. Everybody quickly agrees that if I've got something and I chop it into 30 pieces, into 30ths, that each of those 30ths is slightly bigger than a 31st or a 31st. I'm never quite sure how you pronounce that second one. So each 30th is slightly bigger than a 31st. Yeah, everybody on the page with that, yeah? So one argument that people come up with is, because you're putting together 29 slightly bigger things, and that's pretty close to having 30, so putting together the 29 slightly bigger slices leads to 29 over 30 being bigger than 30 over 31, because you've got, each one is slightly bigger. So that's one argument. A different argument is that if you think about the missing piece, if you think about how far away from one, this is using the measurement again, but thinking about measurement in a different way, how far away am I from one? So when I've got 29 30ths, I'm 1/30th away from one. If I've got 30 31st, I'm 1/31st away from one. And that 31st is smaller than the 30th, so I'm closer to 1 with 30 over 31 than I am with 29 over 30. So one argument is 30ths are bigger, so putting 29 of them together, I'm going to end up with a bigger chunk than putting 30 of those slightly smaller things together. The other argument is one of those is closer to 1 than the other, and the one that's closer to 1 is 30 over 31, then 29 over 30. Talk to the person next to you, which is the correct answer, because they can't both be correct. Okay. I'm not going to say which one's correct. There's some interesting research, I think it's interesting, about the effect of closure on our thinking. It's called the Zárnak effect, and it's named after a psychologist who was Hungarian. And she was very interested in how waiters who didn't write down orders remember what people had ordered. And so she followed waiters and talked to them. And they'd say, oh, I know the guy in the blue check shirt wants an orange juice and baked beans, and the guy in the green hat wants coffee, and so on and so forth. But what the interesting thing that she found was, once they'd served the people the food, 30 seconds later, she'd say, what did the guy in the green hat order? And they'd go, I have no idea. Got no idea at all. Because they didn't need to hold on to that memory. They'd closed the order and the brain shut it down. And there's been lots of research since then based on this, which shows a similar effect in maths lessons, that although as a teacher it's very nice to bring everything to a nice closure at the end of a lesson and say, okay, so we've all got an answer now, and here's the answer, and let's tidy it up. The effect on the learners is as soon as they walk out the classroom door, they stop thinking about the lesson, because you've kind of tied a ribbon around it for them and closed it. So leaving a problem unsolved at the end of a lesson is better than actually reaching a conclusion. Coming back to it the following day, kids will come back with more insight into it than they did literally having slept on it. There's the evidence of sleeping on it as well. The other piece of research I quite like on this is they got adults to come to a psychology lab, and they asked them to come on 2 consecutive days, and they were told that the research was about memory. And they sat them down and they taught them how to create a numerical sequence. So they said, write down 2 numbers, write down a number, double it, add 10, take off 5, add 3, blah, blah, blah. There were several steps they had to go through to generate the next number in the sequence, and then they did the same procedure to that number. And they practiced it in this one-to-one situation until everybody could remember the sequence, said they could remember. And the psychologist said, okay, we want you to go home, and can you come back tomorrow, and we just want to know if you can remember what we taught you. Which was a lie, because that wasn't what the research was about at all. What it was about was there was actually a much, much simpler rule for generating the sequence. They'd made the procedure unnecessarily complicated. But they didn't tell the people in the research. They weren't told that. These people went home, they came back the following morning, and the researcher said to them, can you remember what we did yesterday? And over 80% of them said, yeah, I can, but you know there's a quicker way of doing it. And they'd figured out there was a quicker way of doing it without being told to do that or asked to do that. It's just the brain likes closure, it likes simplicity, and the whole thing about behind the scenes, they weren't conscious of doing it. Overnight, they'd worked on it. So I'm leaving the answer to it open. I'm sure you're all happy. But here's another way you can think about this, which is this. I don't know if anybody thought about this. Occasionally people say, I looked at a pair of simpler numbers. So what's the pattern here? That I've got a number where the numerator was increased by 1 and the denominator was increased by 1. So if I start with a half, that turns into 2 over 3. And I'm fairly confident that 2 over 3 is greater than a half. And 2 over 3 turns into 3 over 4, and I'm confident that 3/4 is greater than 2 over 3. And if I carry on, I'm going to get to 29 over 30 in that pattern. And so if I add 1 to the top and 1 to the bottom, by an inductive process, I'm pretty certain that maybe the pattern will continue as I go through. Oh, yes. And notice what you're doing there is you move to close to 1. Now, of course, a more kind of back to basics approach would be to say, you know how to do common denominators, put them over a common denominator, okay? And you get some gorgeous practice of some fairly ugly multiplications to do in doing that. And you've got a procedure that will work. But I want to suggest that playing with the idea about seeing these fractions as a measure, there's more depth of understanding is going to come by playing with what we've just played with for the last 5 minutes. And looking at those ideas about how do I compare these without kind of just resorting to a straightforward calculation will deepen kids' understanding. And you can do it with young kids. This is an equal sharing problem that I've done with 5-year-olds. 4 hungry children come home from school, they can only find 2 slices of bread, they toast the bread and share it equally. Can you draw a picture? I'm just expecting the kids to know how toast works here. And in my experience, what most 5-year-olds like to do is this. They like to draw the 2 pieces of toast, cut each piece up into 4 pieces, and give everybody one of the pieces. Again, variation. I want more than one solution to play with. So the solution I'm looking for is the kid who does this, or if they don't do it, I produce it myself, which is to say, well, look, you've got 2 slices, you can just cut each one up. Another conversation we have with the 5-year-olds is, this is interesting, because if I'm really hungry, you kids are telling me if I go home with you, I'm going to get 2 bits of toast to eat, and you're telling me if I go home with you, I'm only going to get 1 bit of toast to eat. So if I'm hungry, I know who I want to go home with. And of course the kids are going, no, of course it's not. It's the same. Okay, convince me it's the same. Do some mathematical reasoning. We can cut it out. We can match the pieces. And then I've got a conversation I can go into. So you're telling me that this bit of toast is not the same as that bit of toast. And we're into measures now. And there's a question at the back there. Sir?
Just curious, is there a particular reason why the question says
it's to stop it being quite so floppy. When I say I haven't got any bread, but I've got some cardboard. it's a bit more like cardboard than it is. So it's not the toasting isn't deeply important, but it just adds a bit of solidity to my toast. Yeah. Thank you for raising the question. And then of course we've now got the conversation about, so we need to have a mathematical name for this bit of toast. What is it? It's 1 bit out of 4. What have we got here? We've got 1 bit out of 2, and we're saying we call this a quarter. I've got a quarter plus a quarter is equal to half. 2 quarters is equal to half. I'm doing equivalent fractions. I'm doing addition of fractions, which are ideas that can then take me all the way through. I don't have to wait until those kids are 8 or 9 to do that. We can be playing with that through having that idea centrally from the beginning. Okay, here's another big idea. This was a test that was given to some 11-year-olds. And one of the questions on the test was, there are 2 jars. One's got 25 M&Ms in it. The other one's got 75. Oh, sorry, I changed Smartie. Sorry, I didn't check my slide. This was Smarties. And I said to somebody yesterday, which is going to mean more in Australia, M&Ms or Smarties? And they said M&Ms. So that should. So it's not a trick question. The answer isn't 0. that should say M&Ms. All right, bloody proofreading let me down. So 25 M&Ms, 75 M&Ms. How many M&Ms are in the jar? And unlike, 90-odd%, almost all the 11-year-olds get it right, okay? Later in the paper, there was a question which said there are 2 jars. One contains a litre of water at 25 degrees, and the other a litre of water at 75 degrees centigrade. The contents of both jars are poured into a third jar, and about 70% of the kids think the water miraculously boils. That by putting it together, you get 100 degrees, because they slip into additive. And this is what I want to spend the last part of the talk talking about, is this distinction between, which I was hinting at earlier, additive relations and multiplicative relations. And if I've got one kind of key takeaway message is I want more blue water between the two. I want us to stop, and here's my strong statement, I want us to stop telling kids multiplication is repeated addition. Because what happens as a result of that, sometimes it's repeated addition, but it's actually not repeated addition very often. What results in that is we've got lots of evidence that when kids get into secondary school, the default approach they have is when in doubt, add. That you give them scaling problems where you have a rectangle which has been scaled up, and it might be an 8 by 5 rectangle, and you scale it up to say that size become 10 long, and they go, oh, you've added 2, so the 5 has to become 7 because you add. We muddy the distinction between the two. And I just want to explore why I think they're so different and how we might keep them different. So it's this distinction between additive and multiplicative relations. Traditionally, we talk about addition, subtraction, multiplication, and division, the 4 rules of arithmetic. Lewis Carroll, in answer to looking at, says they are ambition, distraction, uglification, and derision. I quite like the idea of doing a long derision. Along with many other writers, I'm really interested in how we treat these not as 4 rules, but as 2 different ways of seeing the world. Different ways of seeing the world. And let me elaborate what I mean by that. So, If I've got a bag of 7 pairs and I add 6 more pairs to the bag, how many pairs are in the bag? Okay? Calculation you've got to do to solve that is 7 add 6 is 13. Okay? How many in that story, including the answer, how many numbers are there? It's not a trick question. Shout it out. 3. Including the answer, 3. Including the answer. Yeah? 7 and 6 and 13. There are 3 numbers. I'm putting pairs into bags of 7. How many pairs do I need to fill 6 bags? That's 7 multiplied by 6 is 42. Including the answer, how many numbers are there in that story? 3. 7, 6, and 42. That's the trick question. Because in that story, there are actually 4 numbers. And the really important, the important hidden numbers is hidden in bags of 7, and a bag. Here I've got a bag of 7. Here I've got bags of 7. That second problem is a very, very simple ratio problem. There's an implicit each in it. And that's the key distinction for me. We think we don't teach kids about ratio and proportion until they're well up into primary school or even secondary school. But actually, we're doing ratio and proportion in multiplication right from the beginning. We hardly ever give kids a repeated addition problem to do. What I mean by that is this, that if I say to you, put out 4 plates and put 3 biscuits on each plate, that's a ratio. 1 plate is to 3 biscuits as 4 plates is to how many biscuits? If I say there are 5 tables and there are 6 chairs at each table, then 1 table is to 6 chairs as 5 tables is to how many? Don't get me wrong. Kids will solve those problems using repeated addition. They will do repeated addition to get the answer, but those are not repeated addition problems. Here's a repeated addition problem. The door opened and 4 people came in. The door opened and another 4 people came in. The door opened and another 4 people came in. That's a repeated addition problem, but it's different from there's a plate with 4 on it, put out 3 plates, each with 4 on it. And the key difference is this. There's nothing in the door story to stop 5 people coming in next or 2 people coming in next. It's just happened to be the fact that it was 4, followed by 4, followed by 4. Whereas when I'm saying put 3 biscuits on each plate, there's a rule there, which is I can't have 5 biscuits on a plate. I'm doing ratio. Now, the reason I've come up here is I want you to watch my movement. Because I talked yesterday about embodiedness and embodied cognition and how we learn through our bodies. And here's the sense of addition and subtraction that I want kids to get and how it's different from the sense of multiplicative relations. So it's this. If I take that first problem, if I've got my bag of pairs, I put 7 pairs into my bag, I add 6 more pairs, and I'm over here at 13. I might take 2 pairs out and give them away or eat them, or I might add some more. But in that situation where I'm acting out what's going on with my bag of pairs, I'm stuck on a line. All I can do is go backwards and forwards. It's the number line image. That adding, I'm going in that direction, subtraction, I'm going in this direction is the conventional way we do it, and I'm stuck. I'm in line land. I can't get out of this and join you. Whereas when and so addition and subtraction has 1 variable. More pairs, less pairs. That's it. Of course, when I'm thinking about my bags of pairs, I've got an area space to move around. Because in this direction, this is the number of pairs in a bag, but in this direction is the number of bags. So now I've got 2 things I can change. In that problem, I had 7 pairs in a bag, but I might have 9 pairs in a bag, or I might only have 3 pairs in a bag, so I can move backwards and along the line. But I had 6 bags, so I can move this way, or I only had 2 bags, so I can move back, or I had 8 bags. Multiplication, the embodied sense of multiplication and division, is moving around an area because it's got 2 variables. I've got the number of pairs and I've got the number of bags. So it's a 2-dimensional image I have of it, and which is different from the one-dimensional image of addition and subtraction. So I want to not teach multiplication as jumps on the number line. I want to teach it as moving around through space. I'll come to multiplication and division in a moment. I want to very quickly talk about additive relations. So what I'm also keen with this idea of big ideas is what's my kind of minimal kit bag of what do I need as a teacher? I think I don't need very much in the way of representations. So I want, for addition and subtraction, I want to work with part-part-whole relations and number lines, because it's one variable. And that's it. If I use bar diagrams and the number line, that's the entire kit I need to deal with additive relations all the way through school. Because all additive problems are part-part-whole relations. Simple one-step ones, of course, obviously, if I have more than one. And so the relationship between 7, 12, and 5 is represented in that bar diagram. And the other big idea that I want to share with kids is that there are only 3 addition or subtraction problems in the entire world. And those are change problems, collection problems, or compare problems. Some people call these aggregation problems and something else, but I quite like the 3 C's. The change problem, a simple change problem, is I've got 4 muffins. I add 3 more. How many do I have now? I've got 7. 3 plus 4 is 7. I can model it on my number line. I've got 4 muffins. I get 3 more. And it's a change problem because at the beginning of the story, what did I have? I had 3 muffins. At the end of the story, I've got 7 muffins. So something's changed. Mike's got 4 blueberry muffins and 3 chocolate. How many muffins does he have? That's a collection problem. It's different from a change problem because how many muffins did I have at the start of my story? Well, I had 7. And I still had 7 at the end. Nothing has changed in the amount of muffins that I've got. And so that's harder for young children to work with because there's no kind of change to act out. But it's still 4 out of 3 is 7. And compare, of course, is where I've got 2 collections, where Mike's got 4 muffins. I love that. There's a kind of, there's almost synchronized eye padding going on. This could be a new Olympic sport. It's just beautiful. You'll get the slides somehow, I think. I don't know. Yes, Karen's saying yes. And this, if you want to read more about this, search on cognitively guided instruction. CGI is where it comes from. But that's it. You give me any, however hideous the numbers are. If you say, I titrated out, so many milliliters of sodium chloride and I added so many milliliters of water to it, how many milliliters of solution have I got? It's a change problem. Or I put out my sodium chloride solution and so much water evaporated off. It's a change decrease problem. Or, that's it. And I want to let kids into that secret that if I give you an addition or subtraction problem, the first question I want them to ask themselves is, what is it? Is it change? Is it collection? Or is it compare? Because once I've done that, then I can, and that's why I need the part-whole, because that helps me sort out what that relationship is. So Mike's got 4 muffins, Hamster's got 7. I've got my diagram. I'm doing it with a simple problem, but it would work with my titration examples. I'm saying, where does this go? So there's Mike's muffins, which is 4, Hamster's muffins, which is 7, and the question mark there is the missing piece. Now that I've got that diagram, now I've got that sense of the part-whole relationship, I've got a choice about how I do the calculation. Because I can look at that and go, I can now do 4 add 7 is what? 4 add what is 7? Or I can do 7 minus what is 4? Or I can do something plus 4 is 7? Or I can do 7 minus 4 is what? And notice, telling the kids to look for the key word doesn't help me in the slightest here. Because the key word more, which, on that poster over there says, remember more means add, is going to get me completely the wrong answer. But the big idea of what sort of problem is this, and then the second big idea of how do I deal with those numbers. And again, as adults, there's two parts of thinking. We often do them without being aware of it. Let me give you a simple example of what I mean by that. A few weeks ago in England, it's blackberry time. Autumn fruits. I went to a strawberry picking farm, and I was counting my strawberries as I put them in my bag. And on the way home, I put 201 strawberries in my bag. There was 201 in my bag. On the way home, the bag split, and a load of strawberries fell out. And for reasons which I won't go into now, I looked down and I could see that 199 had fallen out of the bag. Okay, I'm one of those savants. Okay. So I'd picked 201, 199 fell out the bag. How many strawberries were left in my bag? 2, okay? I hope you did that. None of you tried to picture 201 with 199 under it and take it away, I hope. You said, what have I got to add to 299 to get to 201? You did missing add end. But of course the story was a taking away story. The story was 200. Now I've seen kids trying to do the taking away there because they haven't done this first stage of saying what's the relationship here and moving on. Okay, and what's behind this idea about the minimal kit bag of representations comes from work in Holland, which talks about a model of, so I'm doing this stuff and I'm drawing these diagrams with kids. So it's me as the teacher is producing these, turning into what they call a model for, where the kids begin to think about this, and draw it themselves, which becomes a tool for thinking. I want kids to have this kind of sense of the part-whole diagram, taking them all the way through school, so that when I'm doing some addition work later on in physics or secondary maths, I've still got this sense of the part-whole. Okay, and so I want to talk about why I want to keep multiplicative relations separate. And the key ideas here is I want from the beginning of schooling to be playing with the idea of simple ratios and scaling. I want to work quite explicitly on the idea that I've got two variables here. And here's what I was saying earlier. If I want to convince kids that 3 multiplied by 4 is the same as 4 multiplied by 3, showing that on jumps on a number line doesn't do it for me, because it's kind of there's coincidence we've ended up at 12 both times. There's no kind of embodied sense of why we got there. But of course, if I've got an array which is 3 by 4, and I can read that and turn it around, and is Jill Cheeseman in here? Jill, are you here? Wave at me. Yes. No, Di's here. Hi, Di. Glad you're here. But Jill was saying yesterday what she does with kids. So I'm stealing it, Jill, wherever you are, but acknowledging it's yours. What she does with kids is she holds that up and says, "Okay, I want you to make what you can see here," and then puts it down. And then when she holds it up the next time, she rotates it through 90 degrees to say, "Okay, check, have you made it?" And the kids go, "Oh, no, it's different." But then they go, "Oh, no, it's the same, isn't it? You've just turned it round." So of course it's the same. So if I'm working with arrays right from the beginning, I've got this strong visceral sense that 3 times 4 is the same as 4 times 3. And so I'm playing with arrays, just talking about them, describing them. I'm getting kids to imagine these in their heads by covering bits up so they can't count them, and so on and so forth. And then, of course, as I move up through primary school, I'm starting to do arrays for multiplication. So if I'm doing 24 times 35, I'll have 20 and 4, an array which is 30 by 5, and so on and so forth. But this is where it can take me. This is why I think it's a big idea that's got mileage, which is this. I'm a big fan of car boot sales. Back in England a few months ago, I went to a car boot sale and I bought an oil painting. And I'm pretty convinced it's a Rembrandt. So I'm hoping to be able to retire very soon. So I got it home and I got some white spirit and cleaned it up, and it's the Laughing Cavalier. So I'm pretty certain it is a Rembrandt. But having cleaned it up, it's looking a bit dull. So before I take it to Sotheby's for auctioning, I decided I'm going to varnish it. And I went to the art shop, and bloomin' heck, decent varnish is expensive, you know, and I only paid £3 for the picture. So I don't want to spend more on the varnish than I did on the picture, so I want to buy the minimum amount of money. Now, this lady's doing what a kid did to me a few years ago, I think. So one of the things I think we don't do enough of, well, maybe we do, but narrative is really important. Yesterday I talked about the concrete, the pictorial, and the abstract as being important ways of working. Narrative, we make sense of our lives through narratives, through stories. So I want to start my mathematics with narratives. But I was doing a problem in a year 2 class about counting jelly beans in jars. And as I was talking about going and visiting a friend who's got a sweet shop and blah, blah, blah. And there was this little girl on the side who in an increasingly loud stage voice was going, "It's not true, you know." He's making it up. It's not true, you know. And it just got louder and louder until I had to stop and say, okay, let's just talk about this, you know. Does it matter if it's true or not? Does it matter if it's toasted or not? And we had this conversation, and the kids were all going, yeah, no, okay, yeah, you know. And as they were going out to play, they were all going, so is it true? You know, they still want to know. So anyway, you can decide for yourselves whether you think it's true. So I went to, I measured my painting. Rembrandt was obviously a mathematician because he painted the Laughing Cavalier on a board which is 3/4 of a meter by 2/3 of a meter. And I went to the art shop and I can get varnish which will cover either 1/4 of a square meter or 1/2 of a square meter or a full square meter. All right. Now, obviously, the painting is less than a full square meter. It's smaller than a full square meter. So I don't need to buy the biggest. Maybe I do have to need to buy the biggest tin and throw some away. But I want to know, can I get away with one of the smaller tins? Because I really don't want to waste any money. And here's where my arrays take me. That is representing a meter by a meter. My picture is 2/3 of a meter, so I need to measure it off using my fraction measures in one direction and thirds by 3/4 in the other direction. So I need to measure it off. There's the bells again. But I know now I'm not Doctor Who, and I'm not going to morph into some other creature when the bells stop ringing. So that's a reference back to yesterday. For those of you who are going, what is this? What is this man on about? My picture is 2/3 by 3/4. Of course, each of those is a 12th. Yes, you're all happy that's a 12th. So that I have to cut the bottom strip off. I have to cut the side strip off, and there's my picture, which is 2/3 by 3/4, and I've got 6/12. So 2/3 by 3/4, and I'm deliberately using the language of by to talk about multiplication, because of this array image, is 6/12, which is 1/2. You do enough of these problems, and some kid will say to you, hey, look, all you have to do is multiply the top and multiply the bottom. But this, for me, grounds in the array where multiplying the top and multiplying the bottom comes from. If that had been 8ths by 7ths, I would have had 8 divisions in one direction by 7 in the other. So I would have had 56ths in there. And if it had been 3/8 by 4/7, that would have been 12/56. So the array, so I can go from with my 4-year-olds baking muffins and looking at the muffin tray and saying, oh, look, this is 3 by 4, all the way through to doing multiplication of fractions. And I've got this continuity of a sense of the big idea of multiplication as this thing that operates in 2 directions, in 2 dimensions all the way through. Now, I said I didn't want to do jumping on the number line for multiplication, but the other image that I'm working with currently, started working with, which is really powerful, is a double number line. So I don't want a single number line, but I want a double number line. And I started getting interested in this. We were giving kids, very young kids, problems about chopsticks. So people are going out for a Chinese meal. How many chopsticks will they meal? I do like chopsticks problems. Not because they come in pairs, but because they're bloody quick to draw. If you're doing flowers in vases, God, can those kids spend ages on those flowers. But there's not a lot of embellishment. You can give a chopstick. So they're great for doing doubling. And we gave the kids these problems, and they kind of spontaneously came up with these kind of double-y number line images, to the extent that one kid did this. And another kid, so we took this and we made this double number line of people in chopsticks as a kind of ready reckoner. This is year 1, 6-year-olds. And then we talked about, so if it's 7 people, how many chopsticks is that going to be? And the kids quickly moved into talking about, oh, look, the number on the bottom is double the number on the top. And so they moved from skip counting into the functional multiplicative relationship of what's the functional here, without using that language. And we were able to say, okay, so if you had 100, if it was 100 people, what would the number on the bottom be? Oh, I don't have to count up in 2s to get there. I know it's going to be 200. If it was 500 people on the bottom, what would the number on the top be? And in fact, there was, we had double 50. That's right, we had double 50. It was 50. I said, if it was 50 people, what would it be? It'd be 100. And these kids said, it's double 50. Does anybody know how we write double 50? And they said, we could write it as 50 times 50, or 50 times 2, or 2 times 50. And we talked about that and agreed that 50 times 2 didn't work. But in fact, this kid, at the end of the lesson, 6-year-old came up to me and said, did you know 50 times 50 is 2,500? I said, how do you work that out? He said, well, I know 5 times 50, I know 5 times 5 is 25, so 5 times 50 is going to be 2. I'd worked it out, I'd figured it out. Rather nice. What I've been playing with now, rather than chopsticks, is jumping frog problems. So for every 1 jump a mother frog makes, her baby frog has to make 2 jumps, and you get the same imagery coming up. But again, here's where it goes to. So as I'm moving up through school, I'm finding that the percentages, I don't know how you teach it here, but in England, percentages are traditionally taught by shading in 100 squares. Yeah, that's the dominant model. But of course, again, linking everything back, what's a percentage? It's a measure. You're measuring against 100%. You've got a percentage ruler is what you're doing, really. So if I do the double number line work that I've been doing with young kids and move it through, I can say if I want to find 60% of 840. Now again, of course, if I just want to teach the procedure, if I want to go back to basics, I'll just show the kids how to calculate, but I'm interested in developing this conceptual understanding. Once I've got the double number line, then it's easy to kind of do things like work out what 50% is, because I just know it's halfway along the line, and I can work out what 10% is, so the 50% is going to be 420, the 10% is going to be 84, and if I want 60%, I'm just going to add those two together. And the sort of problem we've been working on is, this is, again, I was rushing into school this morning. I didn't have time to have breakfast, so I bought an energy bar, and I'm worried about my fat consumption. So I want to see, their different weights, which is the healthiest bar. So these were different bars that the kids had. This was Crew bar, which had per 100 grams, you have 5 grams of salt and 37 grams of fat and 3 grams of fiber, but Blast has got whatever it is, 38 and 5 and so on and so forth. And the kids work on the double number line to do the comparison. That, I don't need to know the percentage of something for its own sake. I need to know it to compare. So here we're working out that 15 grams of fat from 200 grams is going to be 75. And even low attaining kids who are not confident, are working with, they've got 100 grams and 100%, so they don't really need this, but it's helping them see that 75 grams is going to be 75. So I've got work that I'm doing, physically jumping with these frogs, moving into, and then in secondary school, this is taken from some colleagues at London, Daniel Kucherman's work, and if you go, that's a hideous thing to try and copy down. But if you go to the NCETM, which is the UK's National Centre for Excellence in Teaching Maths, and search on Teaching for Mastery Secondary, and these are taken from the multiplicative reasoning materials for professional development they've got there. So there's interesting questions you can ask about this. So one question they suggest is, if a father and a daughter are walking along a path in parallel, which of those is the daughter's steps, and which of those is the father's steps? And then you can talk about, so when are they going to be in step again? When they were in step, when one of them had taken 8 steps and one of them had taken 12, when will they be in step again? What other combinations can you put on there? And then comparing that with, if this line is representing that a US dollar is worth about 12 New Zealand dollars, why is that? What's the same? I talked yesterday about the importance about talking about what's the same and what's different. Just why do those two contexts? They can both be represented by that line, but what's the key difference between them? Just talk to the person next to you. Yeah, okay, so we've got about 3 more minutes, so I'm gonna romp on. So the key, there's lots of stuff you could talk about, but a key difference is, of course, there's some questions you can ask about the second context which don't make sense. So if I say to you, if I've got 3 on the bottom, what's the number on the top? In the steps context, to say when the daughter's done 3 steps, how many steps has the father done, doesn't quite make sense. But in the, although that one might, although that particular number might, but I can say, you know, what's 3 New Zealand dollars? What's 4? What's 5? So I've moved into continuity there, and I can start to play. And again, just as my kids are going, you know, oh look, the number on the bottom is double the number on the top. What I can play with here is that I've got 2 ways of thinking about this, which is the scalar relationship, which is how each line gets scaled up by a factor of 1.25. So I can work out how things move by scaling in each direction. Or I've got the functional relationship, which is what's the function that's linking the number to the top and the bottom. And I'm not far now from taking those 2 lines and making them orthogonal to each other and getting linear graphs out of it. And so I can go from divvying out chopsticks with my 5-year-olds to linear graphs with my 14-year-olds and have a continuity of understanding there by taking those big ideas of this is all about very simple ratios, taking me all the way through. And the last image I want to talk about is the ratio table. Which is, there's my bags and pairs problem, that if I've got bags and pairs, then the multiplicative problem is if I read that, I've got 6 bags, each hold 7 pairs. How many pairs are there altogether? This is multiplication. Talk to the person next to you, what's that problem? What's that story? Okay, so that's I've got 42 pairs. I'm sharing them equally across 6 bags. How many pairs does each bag contain? So that's partitioning. I've got my 42 and I've partitioned it, and it's division as sharing. One of the reasons I like narrative as well, and I want to go back to something I was saying earlier about talking about the full answer. Of course, what I also want to talk about here is what's the answer to that problem. The full answer to the full answer in the world is the answer isn't 7. The answer isn't 7 bags. It's 7 bags of 6 apples. And I want to emphasize that because in that context, division does not make smaller. My 42 hasn't shrunk to become something smaller. It's not that relation. It's partitioned. It's just divvied it up. So, you know, you get kids who later on are given, you know, 12 divided by a half, Oh, the answer to that has to be 6, because division makes smaller. But if I've got this measuring image, if I've got this idea about partitioning, I take my 12 and I have 12 pizzas and I partition it into half pizzas. How many half pizzas? Sorry, that's a grouping image, so I'm going to go into my next one and backtrack that. You need to cut that because that's wrong. But I'll say this one. So here's I've got bags. I've got 7 in a bag. This is the half pizza. This is division as quotitioning, where I know the size. So if I've got 12 divided by a half, so I've got these 2 big ideas of division, which is partitioning. I've got a collection of things that I split up. That's the partitioning. 6. Share them out. But there's also division as quotitioning, which is 6 for you, 6 for you, 6 for you. We tend to do more of the sharing, I think, than we do of the quotitioning. But of course, when you move further up and you're doing 12 divided by a half, kids go, 12 shared between a half. What the hell does that mean? If I've got 12 pizzas, how do I share them between half a person? And somebody told me division makes smaller, so it must be 6. But if I've got this image of quotitioning, the quota is a half pizza, I've got 12 pizzas, and I want to serve everybody half a pizza, how many pizzas do I get? How many people can I serve? Then the answer is 24. But the answer is actually 24 halves. It's not, my 12 hasn't miraculously turned into 24 pizzas. So the context, again, helps me understand what for many kids appears like magic in maths. Half divided by a third. 1.5, in America, kids are taught, I hear somebody say, what is it? It's keep, flip, and change. No, keep, change, and flip. Yes, half divided by a third, keep the half, change the division to multiplication, flip it. So you get a half times 3, and it becomes 1.5. In America, kids are taught to chant, ours is not to question why, just invert and multiply. But of course, if you put that into a context, if I've got half a pint of milk, how many thirds of a pint of milk can I get out from that? I can get 1.5 thirds of a pint. It's the answer to a half divided by a third is not 1.5. It's 1.5 thirds. And if we lose that, kids go, oh my God, I don't have to do any more maths. I can go out and borrow enough money to get half an ounce of gold. I'll divide it by a third, and I'll have 1.5 ounces of gold. Take the half ounce back, take the 1 ounce that's left, half that into 2 halves. Each of those will turn into 1.5. Yeah, fabulous. Yeah, thank you very much. I wouldn't be doing this job. So again, making this ratio, so I'm beating the same story, and the ratio table is just a kind of shrunken double number line and turned around. The double number line, you tend to have everything on both lines. The ratio table, you just revert around. And again, these are just examples of kids using it. But again, what I'm working on here as I move up through school is isomorphism measures. So I've got measure 1 being isomorphic to measure 2, and I can start to explore things like division by the multiplier. If a boat moves 13.9 meters in 3.3 seconds, what's its average speed? And an inch is about 2.5 centimeters. How long is so? If I've started this work of recording these simple problems of apples into bags, I've got something that takes me all the way through. And I just want to finish with something I said earlier on, which is because I can track back, because I've got this history of working with these big ideas, based in kids' everyday actions, everyday understandings of moving along lines, of moving around areas, the embodiedness. And actually, it doesn't mean I lose kids as I move through, because I'm building on what we've already done and continuing developing it and working towards inclusion. Thank you very much for your time this morning.